Hello there. We're going to look at a couple examples, very important examples, related to the discrete time Fourier transform. These are book examples, 4.13 and 4.14 if you want to get a second way to look at them. The first one is an this ideal discrete time low pass filter. Okay, you probably will remember it from 2220. Um, this will look very similar. So if we want to draw the frequency response, we're now using this notation where e to the j omega, the little omega indicates that we're in discrete time. And e to the j omega is sort of is a way to remind us of that. So here's the frequency response for an ideal low pass filter. And it looks like this. Okay, so there's 0. This horizontal axis is of course frequency. And what this says is that within a certain range of frequencies from 0 out to omega c for the cutoff frequency, we're going to pass all signals without any distortion. That's a straight line, so they'll get passed equally. We're going to allow a gain of A. Everything above that frequency is going to be blocked by the low pass filter. All right, so, and this is minus omega c here. The thing about discrete time is that every spectrum of a discrete time signal or an impulse response function, they always are periodic. So we always have copies of this, images you might say, at regular intervals of 2 pi. And so there's one down here at minus 2 pi as well. So these are just replicas of the original signal. Draw in some little markers here. All right, so that's an ideal low-pass filter. Now, why are we passing things at these real high frequencies? We'll talk about this later in the semester, but the short story is that when we send this to the final result to a digital to analog converter, the digital to analog converter is going to have an analog low-pass filter that's going to block all of these replicas. So that's one of the prices we pay for going to discrete time. Of course, if we take the inverse transform and find h of n, we can then apply h of n to a signal x of n using convolution. So we convolve h with an input signal that we want to apply a low-pass filter. And we want to do this for lots of reasons. Typically, there's noise at the high frequencies and we want to get rid of it. And so we can apply this in a microprocessor or a digital signal processing chip using the convolution sum that you are so familiar with. Well, that's our motivation anyway. So right now, let's go ahead and work our way through the inverse transform for this thing. It is defined as 1 over 2 pi integral over any 2 pi range. See, this is periodic, so we can pick any range of convenience of h, e to the j omega. We have to multiply it by e to the j omega n d omega. Okay, so that's the definition. So let's just plug this in for this particular response function here and see what we get. Okay, so we get 1 over 2 pi. We're going to integrate from minus pi to pi. That works for us. And within that range, we're going to pick the non-zero range from minus omega c to plus omega c. And within that range, we just have a constant value for h. It's just a. And we still have e to the j omega n d omega. Well, this is a pretty straightforward integral, and even I remember how to do it. So 1 over 2 pi. We pick up, and we've got a in the numerator. And when we integrate it, we get jn coming into the denominator, e to the j omega n. And we evaluate it from minus omega c to plus omega c. Okay, so let's just write that out. We got a over 2 pi j, j n, e to the j omega c minus e to the minus j omega c. And of course, this is just an Euler identity, and we get a 2j sine omega c. Oops, I left out the n over 2 pi j n. And of course, the things that cancel, 2 and the j cancel, and that 2 and that j cancel. And we end up with a sine omega c n divided by pi n. All right, that's our result for h of n. Now we're not quite done there. One of the things I want you to be able to do that we have to do so often that this is a useful skill is we need to rewrite stuff like this in the form of a sinc function. So our next task, and there's a homework like this, get this into the form of a sinc function. Remember, that's defined as sine pi x over pi x. So it's the sine of an argument over an argument. All right, so how do we do that? It's just a little algebra, and it's not too hard. In this case, we're going to multiply by omega c over omega c, and we're going to do a little manipulation and manipulate. And it's pretty straightforward. It's a little confusing at first, but here's what we're going to get. We're going to get, and we need to do things that preserve the value of this. So we can't do anything that changes the value, of course. So like multiplying omega c over omega c is just 1. So if we do that, let me just write what we get. We get a omega c over pi and sine pi. You notice I need a pi here, pi, but there's no pi in the thing I'm working with. So I can put a pi in omega c, as long as I divide pi out. All right? So I haven't changed the value any, but now I've got a pi there. And I need the denominator to be exactly the same as the numerator. So I can say pi in omega c divided by pi. Right? So now they look exactly the same. Let's see. I've got omega c here and omega c there, and they would sort of divide out because there's no omega c outside of this thing up here. But now there's still no omega c. It's just that we've got it into the right form. There is a pi here, but I've got more pi's than I need. So I move this pi here. I'm going to move it out there. And in here, down here, I have to have the same form as I've got up here. So I've got a pi there divided by a pi there. Well, I think about it. This is the same whole thing as we started with up here. But now we can write this as a sinc function. This is equal to a omega c over pi times the sinc function. And remember, the pi is built into the definition, so I don't have to write this pi or that pi. It's n omega c over pi. And that is our h of n. Okay, now just to keep this in mind, if you don't mind, the sinc function is just an envelope, right? Because the actual discrete time sequence is going to be a sequence of delta functions, and the height is going to be equal to this formula, a omega c over pi times the sinc, as we'll see here in a minute.